So welcome, my name is Yerzhan to the talk Connecting Robot Spinal Cord to the Cloud. I am a recent graduate from Aalto University, master's degree in computer science. I'm working also independently as a system architect with some of my clients. And in today's talk, I'm going to be going a little bit beyond of my work, expanding my work area, covering my interests in cloud and edge computing. So this is going to be somewhere in this area of my interests, where I will be exploring new use cases, new tools around robots and around Kubernetes, and the intersection of two. Speaking of intersections and what I like in my work, in my free time, I like to hang around Thinking Rocks. It's a lab that I'm contributing to and maintaining it at Startup Sauna. We work with different kinds of hardware and hardware systems. And for work, I provide my services through Novel Systems, company that I own fully. So at Thinking Rocks, basically, I'm doing mostly hardware and for clients, writing software, system architecture, consulting. So this also puts it into perspective, my interest in hardware and robots and cloud-native abstractions and tools. And more specifically, for hardware and robots, I'll be talking about robot operating system. And for cloud side, Kubernetes and the tooling and ecosystem around cloud-native computing foundation. So briefly, the content is this. I'll be first covering ROS2, the networking there, then how does it relate to cloud and edge connectivity, and later integration with Kubernetes. And possibly into microcontrollers as well. I did hands-on experience working with this small humanoid robot. It is very, I would say, not cloud native at all. And the problem with it doesn't have any disaster recovery measures. So I had to be very careful when working with it. And when I come in and try to install Kubernetes on it, I have to be aware that if something goes wrong, there is no recovery method, and Kubernetes covers lots of low-level stuff as well, and therefore I'm not actually running Kubernetes on this robot. However, it did spark my interest into exploring more robot operating system, which this robot is running, and that's one tool and one framework that industrial robot and research robot community uses to develop applications around robots, distribute it, package it, and build an ecosystem around it. So after it sparked my interest, I got into working on my thesis, building cross-platform plugin architecture for middleware-based robot system. Middleware-based basically means the robot operating system, and for plugin architecture, I was trying to target porting the whole ROS stack to WebAssembly because when the robot operating system was initially developed, it had a lot of assumptions what kind of platform it runs on, and there is a successful attempt to some extent porting some part of it to the browser. There is an existing ROS2 WASM browser port, but that is done using mscript and toolchain, which targets which predates WASM and targets browser environments more tightly. However, I was going into porting it into WebAssembly with WebAssembly system interface and the component model. Just curious, how many of you in general heard about or know about WebAssembly? Decent enough. So for you, probably it's about like somewhat interesting, but that is more academic area. And I was trying to find more actual use cases for WebAssembly in the industrial environment. That's why I'm also... there are two areas: edge computing, which is more generic, and then more specific application in robots. And robot architecture is more consolidated and makes more sense than generic industrial IoT or whatever. So here is just a brief summary of how it looks like, but I will go into it layer by layer in more detail. So first, how did it all start? Robot operating system initially started as a project in the United States under DARPA funding of some hobbies and people trying to contribute to this new ecosystem around 2010, which means it predates Docker containers. So there was Linux container stuff being developed at the time, and it had some developer experience issues. And of course, when robot operating system was designed, they did not at all consider containerization and other technologies around that. And it took off completely unrelated to containerization technologies and developed separately since then. And however, as everybody else in this world, they come to the problem of portability, abstracting the platform, making less assumptions about in what kind of environment it runs. So after 2014 proposal and release in 2017, Robot Operating System 2 was released, where they set out ROS2 middleware layer as a clear abstraction layer under which they have different messaging systems for implementation of DDS, fast DDS and Cyclone DDS are used in robotics for peer-to-peer shared memory, inter-process communication, low latency, which is very relevant for robots that are tightly coupled in a single system on a single machine. But it may run different hardware, it may run different operating systems. So this ROS2 middleware became the abstraction point for ROS2 to become more portable. And now, after that, after 2013 Docker, containerization and the ecosystem being built, that is built around it, more generic and more, let's say, how to say, more generic platform for isolating your libraries and your applications was developed with containers, where you have your containers as and libraries and dependencies packaged into the system, which somewhat, if we put it into this similar-ish layer, can be compared. However, it is not possible. Well, let's say all of this side in the robot operating system is still just libraries and executables without strict namespace isolation and fault tolerance considered at all. So they're still using CMake, so anybody can link any library, even though they have their own build system. So you may have, for example, robot providers, they ship with their own built binary. Maybe they are skipping the whole ROS stack and directly communicating with the DDS messaging layer, which means you have to maybe dynamically link or statically link to it in a custom way. And you don't know what it is going to do with your machine. You don't have control over resource allocation. And maybe one node within the ROS2 stack starts starving your system out of resources. And as a platform engineer, you do not have much control what happens. But as a robotics engineer, you should be taking care of the whole layer to understand it in order to make sure that the system doesn't break. So ROS2 middleware there becomes even more issue when you are locally developing nodes and testing out features. For example, you may have your robot, actual robot, not in physical world, but in simulation, for example, Isaac Sim. And there is a ROS2 bridge, and you can communicate with a virtual robot, and in your local environment, develop a node which is getting the simulated sensor data, and that way you can locally test it out. You can even test it out in your CI/CD pipeline, and which means you cannot anymore have developers who have different machines run the same stack, which would be running in production. So naturally, you want the developers to start using Kubernetes to have reproducible environments for their development needs. And some crazy people might go into NixOS area, but that will come with its own costs. So it's better to just move the whole thing up and package it into a Kubernetes, into its own container, and use it as a container, because that's what it is designed for. And that's what had been done since ROS2 came about with its tooling, and that's how developers are usually developing their ROS2 nodes and deploying it into production. So under this layout, you can have containers which are running ROS2 nodes responsible for their different tasks, and each container might have one or more nodes depending on what kind of communication requirements they need. So if they want inter-process communication, shared memories, then they are in the same single container. And if they don't need that requirement, then they can be separated. If it is something from the third party that you are deploying, it can be separate as well. You can already start separating it into separate networks, separate machines, and start configuring the networking around that. And that's where Kubernetes starts to become relevant, because you may have different machines running different nodes. You may have single robot, which is running several machines. One Jetson computer responsible for computer vision, another computer responsible for locomotion. And they need to together communicate, and you have different nodes deployed there. And if you want to have control as a platform engineer what and how it is deployed, Kubernetes becomes a very useful tool here. However, in the design of robot operating system, DDS, data distribution service, is designed for very tight networking and tight message exchange. So it doesn't really conveniently extend into our regular cloud containerized environments. And when software engineers in robotics come and start using containerized environments for their local development needs, they usually have the container use a host networking environment directly, which also defeats the purpose of containerization and network isolation in some cases. So in production environment is completely different from what developers are setting up for their local development needs. And data distribution service architecture doesn't really fit. That's why in 2023, ROS2 community came about to try and find alternative, which would address most of the issues related to this, but also other issues, because it appears like ROS2 is becoming too much dependent on the data distribution service architecture. So maybe other vendors or third-party developers are now skipping ROS2 stack and then connecting to DDS, and third-party providers ship their robotic solutions, assuming that if you have ROS2, you probably already have DDS, so it should work. So it becomes a mess. there shouldn't be tight coupling, and as an alternative to the DS, well, before that, this is distribution of the users. You can see that, of course, many developers are using Docker and Podman, but way fewer are going into Kubernetes, virtual machines, and actual multi-machine networking setups. So, but there is that audience which would benefit from that. They were considering a lot of different messaging tools. I'm actually surprised that in the considered tools they didn't have NATs, which would be probably suitable, more suitable than at least MQTT. However, well, MQTT is a brokered, so it's not going to have peer-to-peer messaging. And Kafka is for streaming, and it doesn't really fit into Edge or robotics environment with its purpose. And other tools were considered. However, at the time, there was a tool, Zenoh, that was developed specifically for the purpose of being used at the edge, but being flexible enough to set up different topologies and do not be constrained by being either just broker or either being just peer-to-peer messaging solution. So that Zenoh protocol can be combined to set up very complicated topologies. And due to that flexibility, for example, in NATs, you don't have really peer-to-peer messaging, but with Zenoh, you do have that, even with shared memory. So this is more suitable for robots, and that's what they went with for supporting it as a tier 1 middleware in the previous distribution and in the current distribution, long-term support. They have it as a tier 1 supported messaging middleware. Now that suits beautifully into Kubernetes environment because you can have Zenoh under different networks set up as routers, and they route the messages, and you can have direct connection to what kind of data is being exchanged on your robot from a separate network. And a practical setup would be to use K3s on your robot environment. You could have one K3s cluster per robot, but if you have trusted kind of factory environment where there is a computer server running locally, then you can have a control plane there, and if you trust networking enough, you don't need the control plane on the robots that can be connected to the control plane. However, K3s comes with quite flexibility to set up multi-cluster environments as well. And on your cloud environment, of course, you have more flexibility to choose what kind of Kubernetes setup to have. And Zenoh speaks over TLS router, and it has support, of course, for MTLS encryption, and you could expose it publicly and secure it with MTLS, but that comes, of course, with the cost of you yourself securing it, having the client certificates for the robots, for mutual verification. But more practical setup would be probably to have a VPN set between two clusters, and considering that you might be also running MediaMTX, because robots would be streaming, for example, video data to your cloud environment, and you may have NATs already integrated for messaging layer in your cloud environment. You may have actually NATs also on the edge. Then configuring too much public surface layer for security becomes a bit complicated. So more practical, and I think, in my opinion, secure way is to have a VPN connection. And it is also more convenient for you as an admin to be able to connect to the VPN network and manage your cloud environment separately and your robot separately from the same network. And speaking of creating this cloud and edge environment, now this setup works, can be extended and very flexible. But there are some environments in the factory where you have a machine which is required to run Docker, and you cannot have Kubernetes running on a Docker on an edge device because you have a container inside the container with an orchestration layers that doesn't fit. So in situations where you cannot run Kubernetes at the edge, this talk is very recommended. I really like it, where they are actually integrating WebAssembly as an orchestration tool, and specifically wasmCloud, which is WebAssembly native orchestration tool, which is not at all dependent on Kubernetes, but works alongside it. And you can use it to orchestrate your WebAssembly workloads. And it is less, it doesn't require as many resources as your regular Kubernetes setup, and can run on top of a container in the edge environment or on top of the Kubernetes in your edge environment as well. So, how much time do I have? Yeah. Then, yes. Quick notes then on microcontroller extension, that's the last thing. wasmCloud is dependent on wasmTime as a runtime environment, and wasmTime can be compiled to run on an edge device that is resource constrained, that is not running, for example, that is running resource constrained Linux, for example, OpenWRT on your router. But for embedded devices, there is another runtime, WebAssembly micro runtime, and that is not yet adopted in the WebAssembly world because for orchestration and composability of WebAssembly workloads, it is using component model, and WebAssembly micro runtime doesn't have support for that yet. But Airbus as a company is, I think, promising to bring component model support to WebAssembly micro runtime, which means with that support, you can also extend the orchestration layer up to even microcontrollers, which is even more exciting, and I'm looking forward to that. So that's mostly it. I can answer questions if there is time.